initial value of the measurements are the black boxes. This is for CMS. Now if you look at the decay modes, that's even a more famous plots, are looking at the decay modes where you sum over the different production mechanisms. So the sum implicitly assumes that the ratios are the standard model one. Then you would have different branching ratios. The line here is the 1, the 0, and then you have different measurements. The same thing from the CMS. 1 would mean that you have standard model, so the cross-section times the branching ratio divided by the cross-section times the branching ratio for the standard model. Sometimes this is denoted by mu or mu hat. And the different decay modes with the error bars in the red, the center in the black, and the average in the green. So now what you see is that it agrees pretty well with the standard model. That's the first thing to know. It agrees pretty well in different channels. And most significantly, it agrees in the Higgs to diphoton, which is a loop suppressed process. Okay? Furthermore, it is a scalar. So if you measure the, let's say, Higgs to ZZ star, this goes to 4 leptons, you get this horribly complicated kinematics. You stare at this for a while, and you realize that the initial point is either a scalar with a positive parity or a scalar with a negative parity. If you had a spin 2 with the parity plus minus and so on, the distribution of the leptons in the final state will be different. Right? Just the distribution will be different, so therefore you have sensitivity on the spin and parity of the initial state. And the scalar is preferred over the other options at more than 3 sigma or more than 4 sigma for these more exotic options. So it is a scalar. I think it's quite safe to say it is a scalar, the same thing as in the standard model. Now if you want to go a little bit further away from the experiment and really try to understand what it means for the physics, well, the first thing you can do is you can just write down an effective Lagrangian and see what you're really measuring in terms of the couplings to the gauge bosons and the fermions. So you will, let's say, write this effective Lagrangian. It's a very simple thing. You just write down all terms that you can possibly think of, where you have a single Higgs, so a single Higgs to a WW coupling, single Higgs to a ZZ coupling. The coefficient in front is such that the CV, which is the unknown coefficient, will be 1 in the standard model. We also took the coupling to the W and the Z to be the same, so that's the custodial symmetry. Then you have different couplings to the PV bar, tau tau, CC bar. Now the way this was written down is that the top was already included in this dimension 5 operator. It's down by alpha s over the remaining loop factor, so it's alpha s over 12 pi v. Again, normalized such that this will be close to 1 for the standard model. The C gamma similarly. And then you can also allow for some invisible decays. So I did something very simple. No? I just wrote down all the terms that you can think of, the leading order, so dimension 4 are normalizable, dimension 5 would be the leading couplings to the gluons or the photons, and let's see what the deviations are from the standard model. So what you're really assuming here is that we only have a standard model plus this extra guy, and there's no other light degrees of freedom beyond the standard model which are lighter than 125 GeV or so. As I said, top is included in these two couplings, but I will make it explicit in the following slides. Right? So let's look at the decay widths. So everything was normalized such that at the standard model, these couplings, the effective couplings are 1. So if you find that you're away from 1, This would be new physics. And the three-level decay widths are now normalized to the standard model, where they're just proportional to this extra, the effective coupling. So if you have a deviation in Higgs to BB bar, well, you will change the decay width by CB squared. Now the one loop widths are called kappa G, and these kappa G are, there's a, let's say if you look at the Higgs to glue, the dominant piece is coming from the top. So if you modify the top coupling, there's an order 1 coefficient sitting in front. You could also have other contributions from heavy new states running in the loop. So that again we have a coefficient which is roughly 1 times this new effective coefficient. The contribution from the bottom is much smaller. Why? Well, because the bottom couples with proportional to the mass. The B mass is much smaller than the top. Right? So the coefficient will be smaller. Now if you look at the Higgs to diphotons, there's two main contributions in the standard model, either the top running in the loop or the W running in the loop. So the top running in the loop has a negative sign compared to the W running in the loop. So if you change the couplings to the Higgs to WW, that's the CV coupling, where the coefficient in front is 1.3 or so. But if you change the coupling of the top, the coefficient is minus 0.3 or so. So in the standard.
Explicit assumptions of the new physics of kappa G and kappa gamma for the coefficients, for the delta CG and delta C gamma coefficients. It's an explicit assumption of the contribution.
So that's a free parameter.
Oh, we have a coefficient of 1.03.
It's just the normalization of the dimension 5 operator.
Just happened. Also draw a diagram there.
There's no new physics here. So this delta CG, if you want a new physics, well, this delta CG, there's a coefficient in front, which is this 1.03. Okay. So if you have a new guy, you will have a Wilson coefficient, and this Wilson coefficient will be, if you want to translate to delta CG, you just divide by 1, 0.3. Okay. It's just the numerical factors in the definition of the Wilson coefficient. Yeah, it's nothing hyper. Okay, so as I said, these kappas are dominated by top in the standard model. And I introduced this scaling of the top coupling as CT. And the diphoton is dominated by the W, and the top cancels against it. And these new contributions would be due to extra new physics states that run in the loop. Right? Okay. Now there's also the change in the total width. If you're changing the couplings to different states, there's going to be a change in the total width. The largest contribution will be if you change the Higgs to BB bar, because that's roughly 60%, and so on for the smaller contributions. Now that's important. Why? Well, if you change the Higgs to BB bar significantly, then you change the total width. If you change the total width, effectively you will change all the other branching ratios by the same amount, right? If you want to have the branching ratio, you divide by the total width. If the total width is smaller, the other branching ratios will be bigger. Right? So if you change any of these couplings, it will also change the total width. For instance, as I said, the CB has the largest weight. Now there's a change in the production cross-sections. We had three main production cross-sections which are being probed now. So if you look at gluon-gluon fusion, so glue goes through a top to a Higgs. That's in the standard model. If you have other contributions, we call this kappa G, and the new cross-section will be just kappa G squared compared to the standard model. If you have vector boson fusion, where you have the partons emitting the W's going into the Higgs, or if you change the coupling between the Higgs and the W, this will change this cross section, so the vector boson fusion now will be CV squared or times the standard model vector boson fusion, and the associated production scales the same way. There's a coupling of the Higgs to WW, and it scales as a CV squared. Now the experimental fits, I should say that here there's a big confusion about the notation. So one notation I used, there's other notations. What is used in the fits is these kappas. So the kappa F will be what I call CF, the CV is what will be the kappa V, and the kappa G and kappa gamma is really what I call the kappa G and kappa gamma. Okay? So what you can do is you can constrain now simplified models. Right? You see that there's, if I change one of these couplings, there's a correlated change in the cross sections and the decay widths. So if you want to get the most out of the data, you want to take this correlated change into account. It's only interesting if you do simplified models. If you change too many parameters, you don't have experimental sensitivity right now. Now, an interesting simplified case is, for instance, where all fermion couplings are scaled simultaneously by the same amount. So this kappa F is exactly the same for all species of fermions. And if you look at Atlas, that's the kappa F versus kappa V, the constraints, the combined feeds, there's two regions, the red ones, and then there's many different regions here carved out by different channels. So the blue one is, for instance, from Higgs to gamma gamma. Then the Higgs to BB bar, there's a big blob, and so on. You see that all of them somehow align in the standard model region. So the standard model region, note that is here, right? This cross, the CMS, it's a slightly different picture. So the standard model is this cross here, and the negative solution, which was more prominent for Atlas, is less preferred here. The measurements don't align. So you see that you are close to the standard model, but the difference is sort of a 20%-ish in this kappa V, kappa F. So that was the gain of the simplified model. Before, when you only looked at the overall agreement of data, we were sort of 50% order one corrections were possible. Now you could do something else. Another simplified model is that you only change the contributions to the loops. So I have extra new physics running in the loops, but the three-level couplings are not affected to the Higgs. So that will be a change to the Higgs to gamma gamma and Higgs to glue glue. And you see that the corrections here, this is the standard model, the corrections are at the order of, I don't know, 40% or so. You could also look at the invisible width. So that's denoted by branching into the BSM. And you see that you're driven to a small invisible width versus the coupling to the gluon. So this would be the standard model. There's no extra decays, and the data really prefer no extra decays. Okay, so the bottom line is very correlated changes. If these very correlated changes are allowed, the deviations from the standard model are at the level of 50%. In these couplings, now if more general modifications are made, then even larger effects are possible, with some fine-tuning maybe. But the pattern really is the standard model-like. No? So the thing to really take out of it is that you have these three-level decays, and these are of three-level size, and then there's the loop decay. Loop level couplings are of loop level size. So the CG and C gamma are of loop level size. So there's this 1/16 pi squared sitting in front. So it is like in the standard model. However, beyond this picture of tree level versus the loop size, there are sort of order one effects possible or allowed experimentally compared to the standard model. Now, to learn more, so if you want lecture are, what we did, we looked at the Higgs in the standard model. The data are consistent with the standard model Higgs. Errors are still relatively large. And as I said, lecture 2 and 3, what does it mean for new physics models?
Very nice and clear introduction. Questions?
You consider the situation that the spin standard model physics only changes this Washington coefficient, so these operators, for instance, Higgs to photon, Higgs to gamma, Higgs to global, but in very general sense, of course, this new physics effect could be also generate these higher dimension operators in low-energy effective field theory, or for instance, these higher dimension 6 operators. So in this case, I think this, how to include this dimension 6 operators is not only just to modify this KTG or K gamma or KF, like what people did here. So will you include this in the lecture? Or?
Okay, yeah, so of course I simplify things. So this is a simplified description. You see that this effective Lagrangian is after electric symmetry breaking. Now you could assume more. You could either do the same thing but look at the 8 squared, which would be the dimension 6 operator, so 8 squared glue operators. You could also assume that you have really a Higgs doublet. Then you would have a more constrained structure. There would be a little bit more structure. If you really want, so you're right. I mean, it really depends on what you try to describe. So this effective Lagrangian, which is used by the experiments right now, was only to describe the single Higgs production and the single Higgs decay. Then it suffices, and you don't have to go to dimension 6 operators. Furthermore, it's useful really to go into this, to have the constraints from the simplified modifications. Like you would only assume that it's a glue, or you would assume that it's only, I don't know, top Yukawa has changed, and you want to learn as much as possible from the data. But you're right that if you want to probe better the structure of the theory, you either go to a concrete model, or you could measure different things like a di-Higgs production, and then you would need to have dimension 6 operators.
Yes, because in the general, because this Higgs to gamma can be in the tree level if we don't put some strange condition like this weakly cut gate theory, so then in general it could be even in tree level. So under the generalizations, of course, this dimension 6 operator could also mix with this tree level, with this loop, so-called loop express operators, and this effect are certainly very important, as we already know from having level physics, that is actually this mixing with tree operators to pen operator is very important if we run the scale, the Jhongli scale from this MW to this harmonic scale. So in the sense that I think for this dimension operators, this analysis is very necessary to.
Yeah, very good. So you're touching on something which I'm not even sure I'll be able to cover in the third lecture, so I can just quickly comment. So the question is really how you count these higher dimensional operators, and it really depends on what you assume about the new physics. Now, there's some confusing terminology there, the tree versus the loop and so on. Now, people with the more EFT leaning would know that you really would like to count the dimensionality of the operators, and what really translates is you're referring to this Silch Lagrangian versus the Carver dimension theory Lagrangian counting. It really depends on what you assume that the UV scale where you complete everything is. So, for instance, the Silch, the strongly interacting Higgs, people would assume that there is an intermediate scale. Right? So if you have this intermediate scale, there is a potential that you have also the loop counting in this dimension 5 operators. So okay, this is becoming, I guess, really a bit more technical. So I don't know. You might ask me the same thing after the third lecture. Maybe I'll be able to use my slides to answer better.
Any other questions?
information from this symmetry?
Okay, yeah, I didn't even want to go into the S&T parameters. So essentially, it's why it's useful is if you roughly the deviation is you take the one loop correction, but even not every one loop correction will be allowed. So it's a non-trivial constraint even on the one loop corrections to, let's say, the W self-energy or the WZ self-energies. So it's roughly a one loop size. That's the measurement. It's sensitive to the one loop size corrections. If you have anything which couples would mix the W and the Z at 3 level, it's definitely ruled out, but even at one loop, you're not guaranteed that you'll be completely safe. So that's roughly the size.
Other questions?
You rewrite the Higgs doublet into matrix form, and you say they have a symmetry SU2 direct product SU2, and do this symmetry same as SU2 direct product U1?
Okay, so there's the subgroup is the SU2 left cross U1, which is the gauge. So that you have a standard model gauge subgroup. So it's the SU2 left is completely gauged. The SU2 right, there's the subgroup, which is the U1, and that's the hypercharge. So the subgroup of the SU2 right is gauged. However, you see that if you forget about the fact that the subgroup is gauged, then you have this global symmetry. It's only approximate. It's approximate for two reasons, because part of it is gauged, so obviously it's not a complete symmetry. The other one is that the right-handed fermions are not in the doublets of the SU2 right. So that's the other breaking, is that the Yukawa's break is approximate symmetry. And also the matrices are not symmetric.
Can I ask a question at this stage, although you've been covering, maybe you're covering that. You started with 1964, which is Peter Higgs and company, which is electrically symmetry breaking. And then you, without a change of thought, some pages later you say it also generates fermion bands. These are somewhat accidental. It came out in Weinberg's paper.
Yes, Weinberg is, that's right.
So you have any comment on that? Just saying that the true holy grail is actually electrically symmetry breaking. That was your introduction to this thing. That you, when you went to the standard model, you freely just said, oh, fermion maximum also generates. Please accomplish mass. But these are not the same thing.
Right, absolutely right. Of course, as you know. That's exactly right. Now, this double role of the Higgs is very special in the standard model. So, if you go beyond the standard model, so part of it I have in the third lecture, but you see that sometimes you really have to work hard to give the fermions a masses. Right? So it's not the fact that you generate the masses to the fermion and break electroweak symmetry from exactly the same source. It's not really guaranteed. You know? It's a very nice feature of the standard model. Now, of course, the other thing that sort of I think alluded to is why you have this structure there, where really the structure of the fermion masses is coming from, and so on. So there's, you see that this part of the standard model has many questions hidden behind it as well. So there are probably different questions connected with the electroweak symmetry breaking and to the generation of fermion masses.
So there's another question there.
This is another question, just comment. I think because of the gauge structure, there's no way that you can forbid the Yukawa coupling to appear. So that's why once you have the Higgs, then you must have, unless you have some symmetries to forbid the Yukawa couplings, otherwise.
Right, but the question is, I mean, the size of the Yukawa coupling is the
Well, of course.
So if you want to explain why the top is order 1,
yeah, it doesn't need to be that way.